Alright, chemistry troop. We are still looking at balancing of redox reactions, and we're getting into examples. We've done now 2 examples in prior videos, one of a simple acidic one, a second one which is a much tougher acidic version, and in this case we're looking at balancing redox reactions under basic conditions. So that's the change over here. I'm going to reinforce all the steps that we've been talking about in the prior videos as far as balancing these redox processes. I know it's a lot of steps. And we have 2 mediums. One is acidic, one is basic. We've done examples with acidic. Now we have to kind of look at that other version, or the basic version. So our example here is to basically just balance the following redox reaction. That was conducted under basic conditions. And our reaction here is looking at chlorine gas to produce perchlorate and chloride. So there's our redox reaction, and again we're emphasizing the idea that now we're under basic conditions, and so that's the big difference here that we see. So our first step in looking at our redox reaction is to assign oxidation numbers. Again, we want to assign oxidation numbers, right, so that we can figure out, what is the reduction, what is the oxidation as far as the elements are concerned. So if we go up to the top here, we're going to now assign each one of these. For our chlorine, each one of those chlorines would be 0, since that's in its natural elemental state. If we look at the perchlorate, our oxygens are in that -2 oxidation state, and since there are 4 of them, has a total of -8. That means that this chlorine must be in the +7 oxidation state, or have the +7 oxidation number. Again, remember, the sum of the oxidation numbers should produce the charge on the molecule. So +7 from the chlorine, a total of -8 from the oxygens. That's where that -1 charge comes from. And then we have chloride on the end, -1, it's monoatomic, and so it also has that -1 oxidation number. So if we look at this, actually the same element is being reduced or oxidized. We have a chlorine that is being reduced, and you could look at that as one of those chlorines as our starting material is in that 0 oxidation state, and then it's going to chloride, which is in that -1 oxidation state, and so there's our gain of electrons. And then the other chlorine is being oxidized, meaning that we're starting from 0, but now we're going to +7 for the perchlorate. So there is our loss of electrons. So one of the chlorines is being oxidized, one of the chlorines is being reduced, and we see that from that change in oxidation number. So this helps us to now move to the second step, which is to develop the half reactions for both processes, for the reduction and the oxidation. So if we start with the reduction, we'll be looking at the chlorine going to chloride, starting with that 0 oxidation number and going to -1. So that is our reduction. That's our gain of electrons. And then we now also have the half reaction for oxidation. Looking at, again, that same starting material, but now it's producing the perchlorate, the ClO4 -1. Starting from that 0 oxidation number, for the chlorine, we then go to a +7 oxidation number for the chlorine. And so there is our oxidation. There is our loss of electrons. So step 1, we identify the oxidation numbers so that we can define in step 2 the changes that are occurring, so we can define the half reaction for reduction and the half reaction for oxidation. So basically, now for each half reaction, for each half reaction, we need to balance individually according to steps 2A through 2E. So again, we're going through now the individual balancing of these half reactions. So we'll start with the half reaction for reduction. So that was looking at our chlorine gas going to chloride. So for our step 2A, we balance out elements other than hydrogen and oxygen. So that means we would have our chlorine gas producing 2 chlorides that are aqueous. 2B, we balance out or balance oxygen with H2O. Right here we can skip. Right, there's no oxygen actually in the reaction. Find the same thing happens with C. We want to balance out hydrogen with protons. And we find, like I said, the same. We can skip since there's no hydrogens. And then step 2D, we are under basic conditions. So we want to add hydroxide in the same amount as H plus to both sides of reaction. Where H plus and OH minus are on the same side, we make H2O. But here, there are no hydrogens or no protons, so we can skip. So 2E then says we need to balance charge. With electrons. And so if we look at our charge angle, where we were left off, we haven't really done anything except for the first step, or 2A, by making a 2 in front of the chloride. If we look at our charge, we have a charge equal to 0 for our starting material side, and we have a charge equal to -2 on our product side. So that means we need to basically add 2 electrons so that this is balanced. So we need to add 2 electrons. And that is our balance half reaction for the reduction. 2 electrons plus our chlorine gas produces 2 chlorides. So that one, or that particular half reaction, wasn't too terrible. And that's what we see if we're just talking about simple elements being reduced or oxidized. But as soon as we get into molecules with lots of oxygen and things of that nature, it becomes way more complex. So here now we want to basically apply the same steps namely 2A through 2E for the other half reaction. So now we're looking at that half reaction for oxidation. And that was looking at the chlorine gas being, or producing perchlorate. So now we're looking at that particular reaction, that oxidation. So we just go through those steps again. First step, right, we want to balance out elements. Other than hydrogen and oxygen. That means we would have our reaction now have a stoichiometric 2 in front of the perchlorate. So our chlorines are balanced. Step 2b, we balance oxygens with H2O. So if we look at our reaction, we have 4 oxygens on the product side times 2, that's 8. So we would end up with 8 H2Os on our starting material side. Now that oxygen is done, we can go to hydrogen, where we balance our hydrogen with protons. So if we had from the 8 H2Os, that was really the addition now of 16 hydrogen atoms. And so that is what we would now have on the product side. And step 2E, we now add same number of hydroxide as H plus to both sides of reaction. Where our hydroxide and proton are on the same side, make H2O. So this is again because we are under basic conditions. So that's the big difference here. So looking at our top idea, we had 16 protons added in step prior in step 2C. Apologize if I said 2D there. That should be or 2E, that should be a 2D. So we need to balance out those protons that we added in the step that happened prior. So that means we would need to add 16 hydroxides to both sides of the reaction. So there we've done kind of the first, part of that statement. We add the same number of hydroxides as protons. That same number of hydroxides here as protons would be 16. Right? And that's just coming from the prior step. And so that's why we added 16 protons to either side. Now, where they're on the same side, we make H2O. And this is what we would be seeing here in terms of that right side or the product side of the expression, that we would now have 16 hydroxides on the starting material side plus our 8 H2Os, our chlorine gas producing 2 perchlorates and 16 H2Os. And so we can simplify this just a little bit. To produce this now for our reaction, half reaction here for oxidation thus far, meaning that our 8 waters on the product side are going to disappear. And we'll end up with 8 H2Os on the product side. So we're seeing this water disappear, and then our H2O on the product side basically going to 8. So there's our reaction, our half reaction so far for oxidation, which is now actually balanced. You might ask the question of why do I need this? Why do I need to add the same number of hydroxide as protons, etc.? What's the big deal? We'll realize that for steps 2A through 2C, that we're kind of just under acidic conditions, if you will, right? We add protons to balance out hydrogen atoms, and that's really an acidic idea, protons, right? That is our definition, at least an Arrhenius definition of an acid. So if we're under basic conditions, that means that there can't be acid around, right? If we're under basic conditions, we should have a lot of hydroxide. We shouldn't have protons. So that's why we want to represent the neutralization process by adding the same number of hydroxide as protons. Now, the reason why we add it to both sides is because we have already at this point, before step 2D, we are already balanced by elements. Our chlorine is balanced, our oxygens are balanced, our hydrogens are balanced. So if I just add hydroxide to one side of the reaction, that's going to mess up all the balancing I've actually done, and actually creates a downward spiral. You're never going to figure it out. So once we're done with 2C, once we understand the idea that, well, now everything's balanced, my chlorine's balanced, my oxygen's balanced, my hydrogen's balanced, I don't want to mess with that balancing, but I also want to represent the idea that, well, it's under basic conditions, and there's this neutralization idea. So with the neutralization idea, I add the same number of hydroxide. But from the atom balancing standpoint, that's why I add the same number of hydroxide to both sides of the reaction. I'm adding the same amount of OH to the starting material side as OH to the product side. And in that way, it does not actually change my atom economy or the balancing that I've actually already done. So we're now able to go to step 2E, where we want to now balance charge with electrons. So just to write that reaction where we're at so far again, so we can put in this charge idea. Right, this is where we left off above, and we start to calculate our charge. We have a total of minus 16 for our charge on the starting material side. Right, the chlorines are neutral, and then we have 16 of those hydroxides that are each individually minus 1. And then if we go to the product side, we would have a total charge equal to minus 2. So it's really that difference in terms of the charge that now says that we have to add a total amount of electrons of 14. And that's where we're balancing our charge with those electrons. So we end up with a balanced now half reaction for oxidation to be equal to 16 hydroxides plus chlorine gas produces 2 perchlorates, 8 waters, and 14 electrons. And there is now our balanced half reaction for oxidation. So we now have both of the half reactions balanced individually. So now that we got those two that's going from those steps of 2A to 2E. We can now combine. And that's going to basically our step 3. So now we want to start to combine these processes. And remember, we want to combine the half reactions by making sure the number of electrons in the reduction equal the number of electrons in the oxidation. And this is this nature of, the cross multiply or cross multiplication of electrons. So we look at where we've left off for each reaction. Right, our first reaction for the reduction looks like this, or looked like this, where we left off. 2 electrons was a chlorine gas, gives us 2 chlorides, and then we also had now our oxidation of that chlorine to produce perchlorate. And water, and 14 electrons. So those are our individual reactions. And so here's where we want to cross multiply each one. We can cross multiply the top one by 14. We can multiply the bottom by 2. And so there's our cross multiplication idea. With cross multiplication of the number of electrons. But we could, simplify it a little bit since both are divisible by 2. Where we can just multiply really the bottom by 1 and the top by 2. And so if we do that, we end up with this overall process. Starting from the top, we would have our 14 electrons plus 7 chlorines. Now realize there's also chlorine below, so that's where the 8 chlorines actually comes from. We have 1 chlorine in the oxidation half reaction below. We have 7 chlorines in the reduction half reaction above. So that's where the 8 actually comes from. And then plus our 16 hydroxides is producing 14 of our chlorides plus our 2 perchlorates plus 8 H2O and then 14 electrons. And so now here's where we go to step 4 and remove our redundancies. Right? We want to simplify the reaction. So our 14 electrons is going to disappear, and that should always be the case, right? Because of the cross multiplication step we did in step 3. And so that's pretty much the only redundancies that we see. So we would end up with this now as our redox reaction. But if we look at this, we could simplify it a little more, as everything's divisible by 2. And so what we end up with some more simplification, we end up with 4 chlorines plus 8 hydroxides produces 7 chlorides one perchlorate and 4 H2Os. We can do our charge check as a last check to make sure that we've been doing things correctly. We end up with a total charge equal to -8 on the starting material side. We also end up with a charge equal to -8 on the product side. And so that gives us our overall balanced reaction. We can't simplify it any further. And so if we look at our balanced redox reaction, we would be looking at now basically what we have above, 4 chlorine gases plus 8 hydroxides produces 7 chlorides, 1 perchlorate, and 4 waters, or 4 H2Os. And so that there is our overall balanced redox process, and specifically balanced under basic conditions.